Fantastic. So welcome to the second talk of our VG2 code meeting. We have Till Käufer. We're going to talk about DuCKLinG. Please, the floor is yours.
Yes. Exactly. So I want to introduce you to the Dust Continuum Kit with Line Emission from Graz. So it's a very simple Python tool that I developed during my PhD with Peter in Graz, actually. And so now during my postdoc, when I'm not busy with other things, we're still further developing it to make it more flexible. And so the idea of the code is that we want to analyze mid-infrared spectra of protopentair disks. So if I just show you a selection of James Webb spectra that we have, you can see a large diversity already. So a couple of objects are really dominated by solid state features like silica, forsterite, also amorphous grains. And then other spectra show a lot of emission lines from different molecules. So you have rotational water lines, CO2, HCN, C2H2, and other molecules. And the idea of the code is that you can take one of these observations and you can decompose it into the different parts. So you can identify all the different dust species you're having and their grain sizes. And you can also analyze which molecules are actually present in the observation and what their emitting conditions are. And so I think there are a couple of codes that are trying to do the same thing. And so I think you can order them on two scales. So the first one is speed, so just the computational speed of the model. And the second one, which I call complexity here, I mean with that how much physics and chemistry is actually baked into the model and how realistic it is. And I think on this scale, if you want to analyze James Webb observations of protopentair disks, there are two extremes. So the very simple models are so-called SLAP models. I will talk about them in a little bit more detail later, but they're a single column of gas where you just calculate the emission from one single molecule at a time. And then on the other extreme is Peter's model from 2014. So there's a full thermochemical model where you calculate the abundances of all molecules and the thermal structure consistently, and then calculate the emission from this model and try to find something that matches the observation. And so while both of these approaches have advantages, I think they also have some limitations. So for SLAP models, it's certainly the complexity. If you describe all molecules individually and you just have single temperatures and column density, if you just look on the right on the thermochemical model, this is not how molecules emit in disks in reality. And additionally, these models only describe the gas part of the spectrum. And then the thermochemical model is, of course, great because you can learn a lot about the physical structure and the chemistry and everything involved. But if I just steal a number here from Peter's paper, I think for all models to calculate them and then find the final model that reproduces the observation, it takes a lot of time. So in this case, it was like 10 to 5 CPU hours. So the idea of DuCKLinG is to fall somewhere in the middle. And admittedly, it's much closer to the SLAP models than to the thermochemical models. So we still want to have the speed that we can run millions and millions of models to compare to observations. But we want to have a little bit more realistic conditions. So not just single temperatures and column densities. And we also want to describe the dust emission at the same time. And so the benefit of a simple model is it's so simple we can just explain it on a couple of slides. So this is the model setup. We have different components and we just sum up all these components. So we don't do any radiative transfer. And so for the dust, the model is based on work by Juhas 2009 and 10. And if we just look at the components one by one, first of all, we have the star, which we either describe by a black body or by a stellar spectrum, if you have one. And then if we move inside out for the dust component, the first thing you hit is the inner rim, which we again just describe by a single black body with a given emitting area. And then the rest of the optically thick emission we describe by temperature power law. So we say you have a maximum temperature at the inner edge and then go to a minimum temperature. And we integrate the black bodies along this temperature power law to get then the flux from this component. And you can see already here this brown curve, which is then the total modal flux, is just the summation of all the individual components. And then next to the optically thick emission, we also have thin emission coming from the dust. So we describe this by another temperature power law, where we use now pre-calculated opacities of different dust species of different grain sizes, and then we combine them at the end to get the total flux from the dust. On top of that, we now added a gas component. So we say that the molecules are emitting among temperature and column density power laws, and then we use a large grid of SLAP models to interpolate and integrate in this grid to then emulate how the emission would look like from these power laws. So just a recap of SLAP models. So they just solve very simple equations. So you have the intensity here of the line, which is dependent on the opacity of the line. And so there's in the next line now. And you see here that the opacity at the center of the line is dependent on the column density you're having. And then a couple of just components you can look up at large databases. So you have Einstein A coefficients, partitions functions, and so on. And the other thing is then the line width, where we assume just literature values, basically. And then you can calculate this for different temperatures and column densities for all the different molecules. And this is what was done in previous work here by Aravi 2024, calculating large widths. And then we use these, as I mentioned, to interpolate and integrate for all molecules individually, sum them up at the end, and get the total gas emission. So this is what you can see here in purple. And we just put it on top of the dust continuum to get then the total spectrum. So you can now compare this to observations. And on the next couple of slides, I want to show you the comparison where we compare to SLAB models and how our output also compares to thermochemical models. So first of all, this is an extract of a MIRI spectrum. So this was published by Grant 2023. This GW Loopy, and in black you can see the MIRI spectrum, and we can now fit this observation with DuCKLinG. And so the model post-year distribution you can see here in blue. And if I just go back and forth a little bit, you can see that we can do a very good job at describing this very limited wavelength range. So when we have now this prediction, we can decompose it and see which molecule is emitting where. And you can see that this prominent branch here in the middle, the CO2, then we have C2H2, HCN, and a couple of water lines scattered around as well. But the more interesting part now is that we can compare the conditions we extract to SLAB models, because in this previous study, Grant et al. Used SLAB models to fit these exact same features. And so this is a diagram here where you have temperature on the x-axis and then column density on the y-axis. And these 4 different dots are the different SLAB conditions that we extracted. And we can compare this now with our full posterior distribution. Because we do complete Bayesian sampling, we get a range of possible answers that can explain the observation. And so if I overlap these posterior distributions with the previous findings, you can see that for most molecules it matches very nicely, but there seems to be a temperature difference for HCN. And so if we go back to the observations, you can see that where the HCN feature is, there's also a little bit of other emission from water and from CO2. So when you do this one by one fitting, which is typically done with SLAB models, you just slightly miss the axial flux that is coming from HCN and therefore get different emissions. And so this is just a case to show that our continuous fitting of dust continuum and all molecules together actually has a benefit over simple SLAB models. On the other hand, you have the thermochemical models. And so this is a simulated spectrum done by Prodemo, where we have a dust continuum, and then we have a lot of water lines on top. And so now we use this as a benchmark to see if our conditions we extract from DuCKLinG are actually somewhat represented in more complex thermochemical models. And so again, in blue here, you can see the fit. And if I just start at short wavelength here and just move a little bit around the spectrum, you can see that most water lines are described very well. Maybe there's sometimes a little offset in the dust continuum, but overall there's very nice agreement. So with our simple setup, we're actually able to reproduce these MOX observations. And again, we can compare now the emitting conditions we are getting in Prodemo and also then in DuCKLinG. So this is a diagram where you have radius on the x-axis and then column density on the y-axis, and the temperature is color-coded. And so this line here corresponds to where one individual water line is emitting in the thermochemical model. And we can do that for basically all the water lines and then get this distribution out. So this shows you where water is emitting in the disk. And now we can compare this with the power law that we used in DuCKLinG to fit this mock observation and hope that it's somewhere in the same region. And so the red rounded line here, this is our power law. And if I zoom in a little bit, you can see that, I mean, first of all, radially, we get a decent match, and also column density-wise, we're getting a decent match. The only thing that we are apparently missing is this very inner hot branch. But when we calculate the total flux that is coming from this region, it's comparably small to the rest of the emission. And therefore, if you just fit something with the power law, it will focus on the bulk of the emission coming from the model. So to summarize, we think that our model is a significant improvement over simple SLAB models. And it somewhat represents the conditions you're getting from more complex thermochemical models. And so just to show you a couple of more examples of what we're doing. So on the left is another example where we fitted the dust and the gas together. And I think this model really shines then when you have optically thick molecular emission, when you have these quasi-continua of molecular emission. So it's easily mistaken for dust continuum. But when you fit both together, you can basically distinguish them. On the other hand, you can also just fit the dust if you want. So I didn't really focus that talk on that. But you can, this is an example of PDF 70 by Young 2024. And they fitted the continuum here just with the dust part of the model and then get out the dust composition and the different grain sizes. And on the other hand, you can also run it as in a way similar to SLAB model. So just use the continuum subsective spectrum and then fit the different lines you're seeing in the spectrum. And so with that, yeah, how to use the model. So everything is open source on GitHub. We have a GitHub page here, which has a admittedly very lengthy README file, which shows you how to install stuff, how to run things, how to plot everything at the end. There's a little bit of troubleshooting. And I think it's rather straightforward to use. So if you have a bunch of examples, so you can see how you can run the gas only version, the dust version, and everything of the model. And then there's also a little explanation on what all the different parameters that we have mean, what are typical ranges that might be useful for your priors. So yeah, just feel free to play around. Oh yeah, the address here of GitHub is on the top right, by the way. And so if you want to get started, another option would be we run a hands-on session at the beginning of the year in Ringberg, actually, and everything is still online. So this is also another GitHub repository. And so it guides you basically through the process of setting up your own input files, of running everything, and then you can check with the quiz how well everything is working. And yeah, at the end, it's just 3 simple commands. So we have running the model. It can work in parallel as well with OpenAPI. And if you use our plotting routine, I think you get about 50 plots or something, plotting all the different quantities against each other. And then on the right, I mean, I don't expect you to be able to read anything here. It's just the complete input file we have for one of the models. And it's just supposed to show you that it's rather simple. We just define which dust species we want to have, what are the priors for all the different molecules and parameters we're having, and then a couple of settings at the top and at the bottom. And yeah, so with that, if you want, just give it a try. Just drop me an email. I'm very happy to help. Yeah, and if you have any questions, I'm also happy to answer them.
Thank you very much, Till. It's a very, very cool code. We are open for questions. No questions?
Yeah, if people just want to get started, they can also drop me an email later.
Yeah, so I have I know Lena has a question.
I would actually play bad and ask the same question. How much time do you need? Because it's a really cool code. I agree. How fast is it?
Yes, so one forward model is in the order of milliseconds, so like 5 to maybe 10 milliseconds. And then the retrieval really depends on how complex the observation is. So if you only fit 1 molecule or 2 molecules and a limited wavelength range, you're done within minutes. I think for this example on the left here, which fitted the full, I mean, starting at 5 micron up to 17 micron with many, many molecules. I think we had more than 100 free parameters. I think then the fitting took about a day, but that's, I think, the most we can get. So it's rather fast.
Oh, thanks.
Eduard, please.
Thank you. Very interesting talk. I have a naive question. How do you define rotation? I mean, and inclination angle. They should influence the line width, right? And
yes.
etc.
Yes. So we treat it very, very simplified. I think with MIRI, the spectral resolution isn't good enough that you actually resolve the Keplerian rotation of the line itself. It just broadens the line. So we just convolve it basically with the MIRI resolution and then say, okay, this is probably larger than the rotational width of the line. For the inclination, we just scale the emitting area. So with SLAB models, you always have 3 parameters. You have column density, temperature, but also how large the area is you're looking at. And so we just scale it by the inclination. So there are no optical depth effects of like having larger line of sight through the disk. It's a very simple treatment.
Okay.
I think there's some assumption about the internal line width involved, which is 2 kilometers per second or so. So this kind of scales then the optical depth effects. But as Till explained, we can't really resolve the lines. That would be not possible. and so we don't need to do it. But this is actually, there's one approximation which I'm not sure. I mean, Till, do you know where this value comes from?
I think you mean the turbulent velocity we're using.
Yeah, I mean, because it's also rotationally broadened,
yes.
and that's not really taken into account indeed.
Yes. So if you look at these equations, I think we just assume that the width of the line is determined by the turbulent velocity and the temperature. And yes, I think it's basically based on Spitzer studies, but the problem at the moment is there are two conflicting values. I think some people use 2 kilometers per second and other people use 4.71. And we don't really know where this difference is coming from. And actually last week I ran a couple of models with different values for that. And you can see that your spectrum looks different depending on that, because then different lines get optically thick at different densities. And so it can make a difference. And I think, so I run a couple of retrievals. It can even make a difference for the quantities you retrieve then. So this is something I think people look into at the moment.
Yeah. I also had a question. Is maybe a bit naive question. So when you said like you had like lines for like 120 molecules that you use, how much does the result actually not depend? I mean, do you get the benefit if you use 120 compared to 10, or what would happen if you use, I don't know, lines for like 1,000 molecules? I don't even know if they exist, but it's just like the question is like, you know, what is the degeneracy? Should we be worried about this? I don't know. I really don't know.
Yes. So the 120 was number of free parameters. So it's not the number of molecules. I think number of molecules, we rarely go past 10 or something. So I think in principle, every molecule has very distinguishable features. So it's relatively easy to tell them apart. But because we're running Bayesian analysis, you can actually quantify the evidence for different molecules. So you can run retrievals that include a molecule and then don't include a molecule, and then see if your base factor, for example, increases or decreases. And similarly, on a similar line, I think this table here is for different emitting conditions. So we use these power laws in temperature and quantum density. And here's a little example where you just, for one molecule at a time, you decrease the complexity. So you say that you don't use a column density range, or you don't use a column density and temperature range. And then you look at the base factor and see which one of these models is preferred. And intuitively, I also thought in the beginning that if you just include more stuff all the time, it's always better. But then the base factor actually tells you if this added complexity in parameters justifies the improvement you get in fitting quality. And we can see in this simple case that for molecules like CO2 and water, you need this extra complexity of these power laws. But then if you have HCN or C2H2, basically it doesn't make a difference if you include it or not. And so this way you can start to distinguish the complexity of different molecules in your spectrum.
Thank you very much.
You triggered the only bonus slide I had. Perfect.
Right. Any further questions? Well, this does not seem to be the case, so I think we should all thank Till again for this very nice presentation and for having publicly available codes, so we don't have to always redo everything.